Hello everyone, and thanks for watching Edupedia World Videos. In this video, we'll begin a new topic, calorimetry. In my opinion, calorimetry is the easiest topic you will come across in 11th or 12th because there are really only two formulas and very simple applications of them which turn out to be pretty straightforward. So let's begin with the basic principle of calorimetry. It says that whenever two objects of different temperatures are kept together and eventually they reach the same temperature, then the heat given by the hot object equals heat taken by the cold object. Right, so this means if we have two objects, let's say this one has a temperature 100 degrees centigrade and this one has a temperature 40 degrees centigrade, and we leave them such that eventually the combination has a temperature of 65 degrees centigrade. That means if this 100-degree block gave J amount of joules to get to 65 degrees centigrade, then this 40 degrees block will have to absorb J amount of joules to get to 65 degrees centigrade. This is just basically a fancy way of saying conservation of energy takes place. Right. How do we calculate heat given by an object? That is given by a standard simple formula. Q is equal to ms delta theta, where Q is the heat. It is either given or taken depending on what delta theta is. M is the mass of the object. S is a particular quantity specific to every material, and it is called the specific heat of that material, or sometimes the specific heat capacity. And delta theta is the temperature difference. Hang on, it's not working properly. Yeah, so delta theta is the temperature difference. Now if the object's temperature rises, that means it absorbs heat. That means if delta theta is positive, it absorbed heat. If delta theta is negative, that means the final temperature is lower than the initial temperature, then it released some heat which must have been absorbed by some other material. Now we know that if we take a pot of water and we heat it by 10 degrees centigrade, more energy would be required than if you were to heat it by 2 degrees centigrade. So we know that it has to be proportional to delta theta. We also know that instead of one pot of water, if I try to heat 6 pots of water together, it would require more energy. Therefore the mass is also accounted for. Also I know that if I was boiling a pot of water or a pot of some other liquid, the heat absorbed would be different for the same mass and the same rise in temperature, and this is governed by S, which is specific to the material substance. Again, just like kinetic theory of gases, here also we can look in terms of mass or we can look in terms of mole, and there's another formula sometimes used, Q is equal to Nc delta theta, which is analogous to ms delta theta, where N is not the mass but the number of moles, and C is not the specific heat capacity but the molar heat capacity. Right, so in this case we are talking about number of moles. If we take S and delta theta, if we take M and delta theta to be 1, then S is simply the amount of heat required to increase the temperature of 1 unit mass of a substance by 1 unit degree centigrade. By that logic, C is the heat required to increase the temperature of 1 mole of a substance by 1 degree centigrade. So there is a slight difference between them, and the factor relating them would have to be the atomic mass. Right. So in principle, this completes calorimetry. We'll just show you a little bit of examples and give you a little bit of specific values to make you more familiar. So let's say I have a 2 kg block of aluminium. It has a specific heat capacity of 25 units. And I have a 5 kg block of copper, which has a specific heat capacity of 40 units. And let's say this is at a temperature 20 degrees centigrade and this is at a temperature 80 degrees centigrade. And I bring them together. What is the final equilibrium temperature? So let's say the final equilibrium temperature is T. That means the heat given out by this hot object would be mass multiplied by specific heat multiplied by 80 minus T. Right, final temperature is T, initial temperature is 80, temperature decreases, so it must give off heat. The heat absorbed by this 2 kg block of aluminium would be 2 into 25 into T minus 20. Right, this is the heat given, this is the heat absorbed. These both have to be equal if the principle of calorimetry were to hold. So what that gives us is 5 4s are 250, so 4 times 80 minus T is equal to T minus 20. That gives me 320 is equal to 5T plus 20. 340 is equal to 5T, or it gives me T is equal to 68 degrees centigrade. We can see, as we knew already, that this temperature lies between 20 degrees centigrade and 80 degrees centigrade. Right. Now, this is one particular type of equation of heat in which we are involving change in temperature. However, there are often times when if we give heat to an object, the temperature does not change, the state of an object changes. That is, it goes from solid to liquid to gas. As we heat it, as we cool it, it goes from gas to liquid to solid. Right. So in this case, there is no temperature change. We could have water at 0 degrees centigrade, and when it becomes ice at 0 degrees centigrade, it obviously gives off some heat. Right. But the temperature is still 0 degrees centigrade. If we were to use Q is equal to ms delta theta, it would give us the answer to be 0. But it's not 0 because the state is changing. So when temperature is changing, you use Q is equal to ms delta theta. When the state is changing, you use another formula, which is Q is equal to ml. In this case, Q is the heat due to the change in state of a substance, and m is the mass of the substance, and L is a specific constant called the latent heat. This equation basically just tells us that to convert 100 degrees centigrade of water to steam, we would require twice the heat for twice the mass. But what heat is required for a unit mass, that is given by this constant called latent heat. Now you can have three types of latent heats. You can latent heat of fusion, vaporization, or sometimes you can have it of sublimation. Fusion is when an object goes from solid to liquid or vice versa. Vaporization is when it goes from liquid to gas or vice versa. Sublimation is when it goes directly from solid to gas. Dry ice would be an example. Right. Now some particular values which you need to remember. The latent heat of fusion of water, we are talking about water now, is 3.4 into 10 to the power 5 joule per kilogram. That means to boil 10 kilograms of water from 100 degrees centigrade water to 100 degrees centigrade steam, it would require 34 times 10 to the power 5 joules. Right. The latent heat of vaporization of water is, sorry, this was fusion, I should have said ice to water. In this case it's water to steam. 2.25 into 10 to the power 6 joule per kilogram. Now there's another formula, there's another unit for heat. The standard SI unit for heat is joule, but there's another unit of heat which used to be used before we discovered that heat was a form of energy. Once you discover that heat is a form of energy, it makes sense to use the same units for heat that you do for energy, that is joule. But before that, for heat, a specific different unit was used, and that was calories. And 1 calorie equals 4.186 joule. Right. So in terms of calories, this becomes 80 calories per gram, and this becomes 540 calories per gram. So you know the latent heat of fusion and latent heat of vaporization. Two more quantities you need to remember are the specific heat capacity of ice and water. Specific heat capacity of water is 4200 joule per kilogram per degree centigrade. By the way, in this in kinetic theory of gases, we had to use Kelvin. Here we can use centigrade or Kelvin because delta theta is a change in temperature. Right? When you talk of change in temperature, Kelvin and centigrade are the same scales. This is also equal to approximately 1 calorie per gram per degree centigrade. And specific heat capacity of ice is just half of that of water. So that is 2100 joule per kilogram per degree centigrade, which is equal to 0.5 calorie per gram per degree centigrade. So let's see how we use these formulas in some problems. Let's say we have a 5 gram piece of ice at minus 20 degrees centigrade, and you have 100 grams of water at 30 degrees centigrade, and you mix them together. What is the final temperature? And also a lot of times what will be asked is, what is the final composition? The final composition basically means, is it all ice, all water, or ice plus water? Now, if the final temperature is greater than 0 degrees centigrade, if it's 2 degrees centigrade or 4 degrees centigrade, then obviously it would be all water finally. And if the final temperature is minus 1 degree centigrade, then it would have to be all ice. But if the final temperature is 0 degrees centigrade, then it could be a combination of ice and water. It could be, maybe we have 25 grams of ice and 80 grams of water. Right, we don't know. So first we find the temperature and then we find the composition. So there are many ways to do it. First I'm going to show you the regular way, then I'm going to show you my method, which I feel is slightly quicker. So the regular way would be, we assume that the final composition is all water at temperature T. And if it doesn't work out, if for example T comes out to be either greater than 30 or less than 0, we know we've done something wrong. And then we assume all ice. And then we assume a mixture, a combination of ice plus water. In that case, we know T is 0. Then we'll have to guess that X would be ice and 105 minus X would be water. Let's assume T. In that case, the total heat given will be 100 into, now we could do in terms of both calories and joules, but I will prefer working in terms of calories. So let's do that. 100 into 1 calorie per gram per degree centigrade into 30 minus T. And what is heat absorbed? It is, ice first goes from minus 20 to 0. Right, now remember we have to take each and everything to take it carefully. Water is just going from 30 to T, where T is smaller than 30. Ice is going from minus 20 ice to water at T. So first ice goes from minus 20 to 0. That gives me 5 grams of ice multiplied by 0.5, which is the specific heat capacity, multiplied by 20. This is ice at minus 20 to ice at 0. Now we need ice at 0 to water at 0. So now we need the latent heat plus 5 grams times the latent heat of fusion of water is 80 calories per gram. Plus, now this water goes from 0 to T. So 5 into 1 into T. Right. Now these two have to be equal. So what we get is 3000 minus 100 T is equal to 50 plus 400, 450 plus 5t. That gives me 105. T is equal to 3000 minus 450, that is 2550. And T, if we take this to be 100, it will come out to be 25.5. So it's approximately maybe slightly more than that. We are dividing it by 105, a smaller number, so it will be 105 bigger number, so it will be smaller. So maybe it will be something like 25 degrees centigrade or whatever. Exact value doesn't matter, right? So we got a reasonable answer between 0 and 30, so we knew that this was correct. But what if instead of 100 gram of water at 30 degrees centigrade, we had 10 gram of water at 30 degrees centigrade? What would have happened then? In that case, this would have been 10, so this would have been minus 10t and 300. So we would have gotten 15t is equal to minus 150, which gives me t is equal to minus 10. Right away we know this is nonsense, because we cannot have water at minus 10 degrees centigrade. If it's minus 10 degrees centigrade, it has to be ice. And we can't say it's minus 10 and ice because we calculated it for water. Right? We took the latent heat of ice going to water. If it were all ice, that would not happen. Right? We would have to use a different formula. So instead of solving in cases, the method which I like to use is, I like to bring everything to the same state. Any one state, it doesn't matter. Right? The graph for water goes like this. Sorry. Let's say this is 0. This is 100. So as you give heat to water, its temperature rises, then it becomes 0. Then for a while the temperature is constant as it is absorbing heat to go from ice to water. Then temperature keeps, this is actually a very small amount, the temperature is still 0, but the heat doesn't, the heat gets absorbed. The same thing for 100, and then it evaporates, and then its temperature keeps on increasing. So you bring it to any one state. You bring it to this state, this state, this state, this state, this state, doesn't matter. You can convert all of it to steam also theoretically if you wanted, and the final answer would be the steam. Just bring them all to the same state, right? So our question was 5 gram ice at minus 20 and 10 or 100 gram water. We'll do both at 30 degrees centigrade, right? So instead of taking cases, I can just take them all, let's say, to 105 gram ice at minus 20, or 105 gram water at 30 degrees centigrade, or 105 gram steam at 115 degrees centigrade. It doesn't matter. Just take them all to the same state. Let's say you take them all to steam at this, then both of them will absorb some energy, right? So now you have a deficiency of energy, but you have both of them at the same state. And once you have both of them at the same state, you can calculate how much energy is left or required, and you can just bring them on together and you'll know exactly where they land. You won't have to, for example, if you have two separate things here and here, where will they meet up? Here, here, or here? You won't have to take cases. You just make them meet up somewhere, and then you calculate how much is left. Let me make this clearer by solving this. So what I like to choose is something in the middle. So I'll take 105 gram water at 0 degrees centigrade. I'll just convert everything to this, right? So let me just rub this part. Yeah, so to get 105 gram water at degrees centigrade, the heat given would be, by the way, this is 105 for 105 gram. Then I'll do for 10 and 5 gram. It will be 100, that is this 100 gram water coming to 0 into 1 into 30, that is 3000 joules. So 3000 joules of heat is given. Heat absorbed, will be 5 times 0.5 times 20 plus 5 times 80. That will be, this is 10 to 50 plus 400, 450. So heat absorbed is 450 joule, heat given is 3000 joules. So what is left? Plus 2550 joules. So now what do we have? Now we have 105 grams of water at 0 degrees centigrade and we have 2550 joules of energy. So we'll give this 2550 joules of energy to this 105 grams of water at 0. It might not go all the way to steam, but it will increase its temperature. We'll get 2550 is equal to 105 into 1 specific heat capacity of water into T, whatever the final temperature is. We see that the final answer is exactly what we got earlier. What if this were 10 gram of water? Then this would be 15 gram water. This would be 10 multiplied by 30. This is 300 and this is 450. So in that case, the heat given is 300 and the heat absorbed is 450. So what is the heat left? It is minus 150 joules. Minus 150 because you absorbed more than you gave. So now what do we have? We have 15 gram of water at 0 degrees centigrade and we take 150 joules of energy from it. If we took a lot of energy from it, it would convert all of this water to ice and decrease the temperature further even below 0 degrees centigrade. But I can see there's not enough energy to do that. 150 joules will be able to melt. 150 is M into L. L is 80. That means M approximately will be equal to 2. So what will happen is approximately we'll have 13 gram water at 0 degrees centigrade and 2 gram ice at 0 degrees centigrade. In the previous method, what we would have done was calculated by the normal method, see that T comes out to be minus 10, which is absurd. Then we assume that it's ice and water together. Then the temperature is 0. We assume that X is ice and 15 minus X is water. And we'll be able to calculate that X is equal to 2. Right. The ultimate point is this. I'll just show it from this graph because it's easiest to explain. If you have one particular quantity here and you have another quantity here, and this is giving heat and this is releasing heat. If it were a straight line, you could just easily do it, but because there are state changes in the middle, it causes problems. So instead of taking this absorbing a little heat, this giving a little heat, absorbing a little heat, giving a little heat, absorbing a little, finding out where exactly they fall in the middle, you have to calculate it for both of them. Instead, you just bring them together. And if you bring them together and the heat left is 0, that is your actual answer. But more often than not, if you bring them together at some arbitrary state, there will be some heat left or some heat absorbed. And then from that point, you can see, okay, this is where I got them. This is the total amount of heat left, so it will go up. Or this is the total amount of heat it absorbed extra, so it will go down. I urge you to solve this particular question by choosing a lot of other arbitrary points as well. Take it all to steam at 100 degrees centigrade. Take it all to ice at minus 50 degrees centigrade. You'll find that once you bring them together, it's a mere matter of traveling down this line or up this line to find out where our substance is. This completes calorimetry. Thank you.